In this video, I shall be discussing some topics from chapter 4, that is chemical kinetics. First, let us know what is chemical kinetics. So, chemical kinetics is a branch of chemistry that deals with the rate of chemical reactions and also the factors that influences the rate of chemical reactions. The next one is rate of a reaction. Okay, rate of a chemical reaction. Rate of a chemical reaction. It can be defined as the change in the species, either reactant or product, per unit time. Okay, now we write as rate of reaction is given by the change in concentration. Okay, change in concentration. It will be either of the concentration of reactant or concentration of product divided by time. Okay, or we can write individually, that is, if it is for reactant, we shall write decrease in concentration of reactant divided by time, because see, for any chemical reaction, if reactant is converted into product, then with time the concentration of reactant will decrease and the concentration of the product will increase. Okay, therefore we write rate if in terms of reactant, if it is in terms of reactant, when it will be decrease in concentration of reactant divided by time, and if it is in terms of product, then we write increase. Okay, increase in concentration of product divided by time. Okay, let us take one example. Suppose reactant gives product, then that rate is given by minus delta R divided by delta T, or in terms of product we can write delta P divided by delta T. Okay, here the negative sign represents the decrease in the concentration for reactant, because see, when the chemical reaction is under process, the concentration of reactant will decrease. Okay, that's why we show it by minus sign. Okay, then in case of the product, the concentration of product increases with time. Okay, over the during the chemical reaction, that's why we have plus sign. Okay, then let us try another example. Suppose A plus B gives C, then the rate will be, okay, the rate can be with respect to A or with respect to B or with respect to C, that is the product. Okay, this is how we write. Now I'll give you one problem. Okay, that one you try it. That is, see, for the reaction of PCl5, okay, PCl5, this is gaseous, will give PCl3 plus Cl2. Okay, now all of them are gas. Okay, so you write the reaction for, you write the rate of reaction for this particular reaction. Okay, then suppose, see, so far whatever we have discussed is for those reactions that have the stoichiometric coefficients same. Okay, that have the same stoichiometric coefficients. Okay, now let us see for those reactions that is involving different stoichiometric coefficients. Okay, so for example, okay, so this one you complete it, rate equals to, you have to write it by yourself. Okay, you do this one. Then now the next one is for different stoichiometric coefficients. Suppose A times of reactant A, B times of reactant B gives C times of, okay, or this much mole of reactant with this much mole of product, okay, will give this much mole of product. Okay, this much. So the rate can be represented by minus 1 by A, okay, del A. So we will divide that stoichiometric coefficients with the respective species, either of the reactant or the product. Okay, this one will be minus 1 by B delta B divided by delta T, which is also equal to del 1 by C, okay, delta C divided by delta T. Okay, now I'll give you one task. Okay, so you try out that one by yourself. That is 2 and 2 of 5. Okay, will give N2O plus O2. Okay, I think it's NO2. Yeah, NO2. Okay, so now you balance it. This one is half, this one will be 2. Okay, I think if you don't put this one also, still it will be fine. Okay, yeah, this will do. Okay, now suppose if you put here 2 and 2 or 5, for this also you do. Okay, so 4 NO2 plus O2. Okay, so you do, you find out the rate of reaction for this as well as this one. Okay, now moving on to the next one. Okay, that is instantaneous rate. So far whatever we were doing was for the average rate. Okay, for average rate we represent it by this form. Okay, this one should be delta. Okay, delta T. Okay, now for the instantaneous rate, see, suppose for example, if a vehicle moves or travels from one distance, from one point to another point with certain velocities, it doesn't mean that that velocity will have always, suppose if you are traveling, it doesn't mean that that particular vehicle will not, will always have the constant or the same velocity or speed. Okay, so it may change sometime. Okay, now in that same way, even in the rate of even in chemical reactions, the rate will not be always same. Okay, so at some point there may be some changes. Okay, so it may be slow, it may be fast. Okay, so in order to find out the rate of reaction at that particular time, we find out by the instantaneous rate. Okay, so that is, so for instantaneous rate we represent it this way. Okay, that is see the rate, that is the average rate. Okay, average rate, we just represent it like this, suppose for example. Okay, now this x can be either of the concentration of the reactant or the product. Okay, now for a small change, okay, before that let me give you the definition. The rate of change of any one of the reactant or product at a given time is called the instantaneous rate. Okay, or instantaneous rate of a reaction. So this, now for this one, this is the average rate. Okay, we represent it this way. If we consider a small change in the concentration given by del x, okay, for a small or for a very small time interval, that is del t, then we can represent by the differential calculus, that is rate is equal to dx by dt. Okay, or we can also write like this, see, limit del t tends to 0, okay, del x by del t will be equal to dx by dt. Okay, now suppose for a chemical reaction, okay, in order to find out the instantaneous rate, suppose a chemical reaction A gives B, then the rate will be equal to minus del A by del T is equal to del B by del T. Okay, this is how we write. Then if it is of different stoichiometric coefficient, or if there are 2 moles of, suppose if this is a reaction AB AA plus BB gives C, then the rate will be equal to minus 1 by A del A by del T. Okay, so the only change that we made between the average rate and the instantaneous rate is with this one. Okay, there we use delta, here we are using D. So here 1 minus 1 by B, D of B by dt is equal to 1 by C, D of C by dt. Okay, so this is how we do it, how we represent the rate. Now I want you to try one problem. Okay, for this one, that is the reaction is N2 plus 3H2 will give 2NH3. Okay, so you find out the rate for this one, or the instantaneous rate for this particular reaction. Okay, now moving on to the next one, that is the law of mass action. Okay, according to the law of mass action, okay, the rate of reaction, okay, or in other way, say at a given temperature, just with law of mass action. Okay, so at a given temperature, the rate of chemical reaction is directly proportional to the product of the molar concentration of the reactants. Say suppose, for example, A and B reacts to give C, then the rate is directly proportional to the product of the molar concentration of the reactants. So it will be A and B. Okay, now this is the proportionality symbol, we replace it by proportionality constant, so K, A and B. Okay, now this K is called the rate constant. Okay, rate constant, K is called the rate constant. Okay, then suppose if it is like this, if it is AA plus BB and CC, then the rate will be based, according to law of mass action, the rate will be equal to K of A. Okay, the stoichiometric coefficients will be raised to the power, okay, like this, and B also will be like this. Okay, now I want you to try one example. Okay, so that is N2O5 dissociates to give N2 plus O2 half. Okay, so you try out this one, then you find out the rate for this particular reaction. Okay, and also for these two reactions you find the rate according to law of mass action. Okay, now the next one is order of reaction. Okay, yeah, order of a reaction. So it is defined as the sum of the powers, okay, to which the concentration terms are raised in the rate law equation to express the observed rate of the reaction. That means, see, suppose this is a reaction, okay, and according to rate law, okay, rate law equation, that is rate is given by A, okay, and B. Okay, so the order of reaction will be equal to the sum of the, okay, the sum of the powers. Okay, so we will have to add these two powers, and whatever number we will get, that is the order of the particular reaction. Okay, say suppose, for example, say in this case N2O5 is NO2 plus Okay, so here the rate is like this, K and N2O5, isn't it? Now the power is 1. Okay, the power is 1. So here the order of reaction, okay, the order of reaction is 1, and this one we call it as first order reaction. Okay, this is called first order reaction. Then if the order of reaction is 2, we call it second order of reaction, and so on. Okay, now I want you to do one problem, okay, for second order reaction. Okay, so you have to write the rate as well as the order, okay, like this. You have to do like this. Okay, so let us try. Okay, that is 2NO2, okay, will give 2NO plus O2. Okay, you find the rate and the order. Okay, then the unit. Okay, so let us find out the units, the SI units. Okay, the units of reactions. Okay, yeah, reaction rate, I think. Reaction, no wait, of rate constant. Okay, we are going to find out the unit of different quantities. Okay, so let us first find out the unit of rate. Okay, we know that rate is equal to change in concentration. Okay, change in concentration divided by time, isn't it? So concentration, either it is for reactant or product, the unit will be same. Okay, now the concentration is in terms of molarity. Okay, so the concentration is in terms of molarity. Okay, so it will be mole liter inverse, and the time unit is second. Okay, so rate will be change in concentration. Okay, so concentration unit is mole liter inverse, and time is second. So this second, if you bring up, it will be mole, okay, liter inverse, then second will become second inverse 1. Okay, now next one is to find out the unit of rate constant. Okay, so the rate constant unit will differ from, depending upon the order of reaction. If it is for first order, then see, suppose the reaction is like R to P. Okay, so it will be, see, the rate will be equal to K and R. Okay, so if it is only of one order, so it will be power 1. Okay, you don't have to write this one. So K is equal to this one, you transfer this side, it will be rate divided by R, isn't it? Now we already got the unit for rate, that is mole liter inverse second inverse, isn't it? Then the concentration is mole liter inverse. So see, mole liter inverse cancel, so the unit is second inverse 1. That is for first order. Now I want you to find out for zero order, okay, and second order. So for zero order, the rate will be like this, 0, and for this one the rate will be equal to Kr power 2. Okay, so you find out the unit of rate constant for zero order and unit of rate constant for second order. Okay, now moving on to the next one, that is the molecularity. Okay, so here molecularity is the number of reacting species. Okay, that is the reactant. Okay, so number of reacting species, that is the reactant which collides simultaneously to bring about a chemical reaction. Now say for example, okay, H2O2 gives H2O plus half O2. Okay, molecularity of a reaction. Okay, Now here the molecularity is, see how many molecules are involved, only one, isn't it? So molecularity is equal to 1. Now this one we call it as unimolecular reaction, because only one, isn't it? Only one molecule reaction. Okay, if it is 2 it will be bimolecular, if it is 3 it will be trimolecular, and so on. Okay, now I want you to find out this one, that is 2NO plus O2 gives 2NO2. You find out the molecularity for this particular chemical reaction. Okay, now next one is the rate determining step. Okay, see, in a chemical reaction, at some point the chemical reaction may be slow, I mean the rate may be slow, at some point the rate may be fast. Okay, now in order to determine the step, okay, I mean in order to determine the rate, either we will follow the slow step reaction or the fast step reaction. Okay, so here we shall consider the slowest step, okay, as the rate determining step. Okay, or the slow reaction will be considered as the rate determining step. Okay, and also before ending the video I want you to have some basic ideas. Okay, before we move on to the next topic, I want you to have some ideas about the molecularity and order of the reaction, and also the factors responsible for the rate of reactions, okay, or rate of chemical reactions. There are some reasoning questions that you have to learn, so we shall find out in the later class. Okay.